In the previous video, we saw the self-inductance of an inductor is L equal to the change in magnetic flux divided by the current. We found that the magnetic flux, for example, in a solenoid, is the magnetic field times the area of one of the coils, this PR squared, times the number of coils. And we found magnetic field is equal to mu naught times the current divided by L and then times the number of coils. So we can substitute this with here. We have we have L is equal to the magnetic flux, that is this would be P R squared N, and then this B, that is mu E N over I and over L. I cancel the I's, and this is the self-inductance. There are many ways to express the self-inductance, and we will talk about self-inductance, mutual inductance in many videos with many applications. But here I want to introduce how to handle differential equations for a circuit, a RR circuit. That is, we have, let's say, a resistor, inductor, and the battery. So first, when we are constructing a RR circuit, we make it the geometry in a way in which the area of the inductor of the box that has the inductor is quite large compared to the voltage, the resistor, and everything else. The switch, we have here a switch, wherever it be. Because we want that only the inductor has the contribution to the magnetic flux. The electric field, we have electric field in the battery, in the resistor due to the voltage drop, and the current flowing here, and we have no electric field in the inductor because the resistance in the wire is practically zero because the wire is so thin. So we can say that the only electric field that we have is produced always in the battery and in the resistor, not here. So we can say that the maximum current would be voltage divided by resistance, the resistance being the resistor, or if the resistance in the wire is taken into account, then we can now define this R as being the sum of this resistance. But anyway, we usually talk as if this were practically zero. Now, when we're dealing with our circuits, we need to find the differential equation. We will do this by Faraday's law that says that the closed loop integral of E dot CL is equal to the negative time derivative of the magnetic flux with respect to time. And this would lead us to a differential equation. Here, the change in magnetic flux would be replaced by Li, here, sorry, L d I in dt, the negative of this. For approaching this, as opposed to when we study Kirchhoff's loop rule and many ways to how to handle circuits, we introduce like 3 ways of how seeing the voltage. This same equation, usually here we had a 0 because we did it with Kirchhoff's loop rule. We certainly didn't have the inductor. We used a different approach that we will use here. Here we will use the approach in which we will construct this equation using the direction of the electric field. So here, the electric field goes from positive to negative. The electric field here goes from positive to negative. So here is the electric field. And the inductor has 0 electric field. The current goes in this direction. So in this in this approach, we are not guessing the current as we did in other videos. So here we can construct the closed loop integral of E dot dl would be just let's say from here all this way to here. This is the closed loop integral. So I have, if the inductor is 0, here I have a resistance and current, and then here I have a negative electromotive force. It is negative because we're going against the electric field. This is the equation. Now if we equate this to this, we have a negative L di dt. So this is the differential equation because here we have I and here we have the I in dt. This is the correct differential equation. We can rearrange this and say Ri minus E EMF plus L di in dt is equal to 0. This is a terrible mistake that most of the physics books happen to have. Not the Bibles like the Sears, but many physics teachers and many books use this as if this circuit is held by Kirchhoff's loop rule, and so they want to equate the closed loop integral of E dot dl equal to 0, and it is not equal to 0. It is to the change in magnetic flux, time derivative of the change in magnetic flux, that in this case, because we have an inductor, it is not 0. And also, here when we take the closed loop integral of E dot dl, it is not this. It is just this because the self-inductor has no electric field. In this equation, if we get to this equation, not from arranging this passing through the other side, but from the bad or wrong reasoning of the books that committed this mistake, the first mistake is that they equate this equal to 0, just because they think that Kirchhoff's loop rule continue to hold. And the other is that they think, or they use as a rule as if there will be a electric field in the inductor, and this electric field has a voltage drop of L di in dt. That it is not true. The electric field here is 0, so this part is also wrong. But if we attach here a voltmeter and we measure the voltage drop or voltage difference from here to here, actually what the voltmeter would measure would be this quantity, L in di dt. But that does not mean that there is a voltage drop here because of the electric field. The electric field in the inductor is 0, and the closed loop integral of E dot dl in circuits in which we have inductors is not 0, because there is a change in magnetic flux with respect to time, that is not 0. So this is very, very important. Now that we have the correct equation, that is this over this, but this because we arrange this passing it through this side, not because of wrong reasoning. Now we can solve the differential equation. There are many ways of solving differential equation. One is to try to do separation of variables, but the other is with the integrating factor. That is my preferred method. So remember that the first order differential equations can be written as we have a, let's say, y prime plus a polynomial of x, y is equal to other polynomial of x, something like this. In this case, I prime would be di in dt. We want this term to be alone, the di in dt, so we will divide everything by L. So here we have R over L, and my Y is I. And this is equal to the voltage or the EMF divided by L. And this is now a first order differential equation. So with the integrating factor, we have the E of the number E to the integral of the polynomial of x. So remember that the integrating factor is E to the integral of the polynomial of x with respect to, could be 2 dt, in this case dx. So here it is R L dt. So it is just E to the R over L t. This is the integrating factor. So here we will multiply this equation by the integrating factor. We have E to the R over L t times the I in the t, or if you want you can put I flux as Newton did, the notation Newton, or I prime for Lagrange, or Leibniz as here, plus E to the R L t R L over times I equals to E, the voltage, over L times E to the R L t, R over L times t. So we recognize that this is just the derivative of the product E to the R over L t times I, because if we take I being a function of t, of time, if we take the derivative, we will have this times the derivative of this, so E to the R over L t di dt, and then this I times the derivative of this, that it is R over L times E R to the R L t. This is exactly what we have here. So the derivative of this is equal to just the, I will put V, no, to don't confuse the E's for voltage, V over L times E to the R over L t. We will integrate this with respect to time, so we can cancel this derivative. We just have E to the R over L t times the current is equal to the integral of this with respect to time. This is just a constant, so V over L. And the integral of E to the something is, remember, E to the R over L t, and then you need to divide the inverse of this, so it would be times L over R. So we cancel the L's. Oh, and a plus C here. Now let's divide everything by E to the R over L t, because we want to find the current. We are solving the differential equation for the current. So the current is V over R, this dies with this, and here we have a constant E to the negative R over L t. Now we know that V over R is the maximum current, and I did not say this. We have a self-inductance here that is L due to the inductor, and the self-inductance is fighting the change in current. That is, when we have the battery turned off, we have no current, so at t equals 0, the current is equal to 0. When we turn on the battery or we close the switch, the current is increasing, but not abruptly. It increases slowly because the self-inductor is opposing to the change in the current. Because the current, when we turn on the battery or when we close the switch, we have current that is flowing through this solenoid, and so this current produces a magnetic field here, and this change in magnetic field in turn produces a current. This induced current is called the eddy current, and this goes in the opposite direction to the current that created this magnetic field. So for that, always the self-inductance will be opposing to the change in the current. If now we turn off the battery, the current will not decrease abruptly, it will decrease slowly because of the same, but now the current directions are the opposite signs of what they were before, but in each other they are opposite always. So if we turn on the battery and we let it turn on for a long time, the self-inductance has a maximum value. So at infinity time, when t tends to infinity, I tends to the maximum current, and that maximum current is as if it were no inductance, and it would be just the voltage divided by this resistance. So this is the maximum current. So V over R is the maximum current. We can substitute this by maximum current. Now, when we have t equals 0, remember that when we have this differential equation, now we need to find C. We can only find C if we have the initial conditions. We know that at t equals 0, the current is equal to 0. So we have 0 is equal to V over R plus C to the where everything to the 0 is just 1, so plus C. And so we have that C is equal to the negative of V over R. And V over R is the maximum current. So we have I is equal to the maximum current times 1 minus E to the negative R over L T. And this is the solution to the differential equation for a NR circuit. So we usually need to know what is R, what is L, and then we can find the current at any point if we know at which time we are taking it. And if we know the current, we can know the induced EMF, and now we can know everything. It is very important to know what is R, L, because at the time equals to L over R, then I have E to the negative 1, and that just means that the maximum current dropped 1 unit of E, or dropped by a factor of E. So that's important. Here we solve the differential equation. Now suppose that we drop the battery. We have no battery. Now what would be our new differential equation? We will do it the same way. Now the closed loop integral of E dot dl continues to be equal to the change in magnetic flux with respect to time, but now E dot dl is just the current times the resistance, because now we have no battery, and this would be equal to the self-inductance, the negative of the self-inductance, times the change in current in dt. And now we need to solve for this new differential equation. This you can also solve this by integrating factor, but this is reasonably easy to solve with separation of variables, so let's do that. We have, let's say, negative R over L dt is equal to 1 over I the I. So integrating both sides, we have negative r over lt is equal to the natural logarithm of I and then plus c. We elevate e to these powers from both sides to cancel this. We have e to the negative r over lt plus c is equal to e to the logarithm of I is just I. And this you can separate them and put times, sorry, e, I'm using it like this, e to the c that is just again a constant, so I can call it just a constant